When you listen to a complex lecture or a favorite song, your experience is entirely powered by invisible, formless vibrations floating through the air. How do those invisible ripples penetrate the dark, silent vault of your skull to create emotion, focus, or a sudden realization? Right now, as you process these words, there is a second operation running constantly. Your auditory system is conducting a completely silent 24/7 background check just to keep your body sitting upright in your chair. This structure operates as a dual-axis radar system, integrating raw acoustic frequencies and precise spatial telemetry into a single biological feed. Looking at this diagram of the outer ear, the first step is physical capture. The fleshy outer part, called the pinna, acts exactly like a satellite dish. It sweeps up surrounding sound waves and funnels them down into the narrow tunnel of the ear canal. At the end of that tunnel, the waves hit a dead end. They strike a highly sensitive barrier known as the tympanic membrane, or eardrum, forcing it to vibrate in a precise rhythm. Behind that pulsing membrane sits a mechanical amplification chain made of 3 tiny bones: the malleus, the incus, and the stapes. The stapes actually holds the record as the absolute smallest bone in the human body. To keep this microscopic lever system from breaking under pressure, the body uses the Stapedius. At just 1 millimeter long, this tiny muscle acts as a stabilizer, holding the fragile bones steady while they rapidly vibrate. The entire point of this intricate micro-engineered chain is leverage. It takes relatively weak air vibrations and drastically amplifies their force, making them strong enough to breach the dense inner ear. Once inside the inner ear, the amplified vibrations hit a snail-shaped organ called the cochlea. As you can see in this cross-section, the cochlea is filled with a specialized liquid, and the stapes bone knocks directly against it, sending ripples through that fluid. Inside the cochlea, rushing fluid washes over thousands of microscopic hair cells. As these structures bend with the current, they convert the mechanical energy of the wave into active electrical signals. At this point, the mechanical journey of sound is over. The newly generated electrical signals exit the ear entirely, shooting up the auditory nerve. They arrive at the brain's processing center, specifically this highlighted section called the temporal lobe. Here, the brain decodes those raw electrical pulses, organizing them into a recognizable pattern, like a car horn or a friend's voice. The ear itself doesn't actually hear a thing. It is strictly a translation device, gathering and formatting the raw data the brain needs to assemble the final experience of sound. But there is a second access to this radar system. If we look back at the inner ear and focus just above the cochlea, we find 3 separate fluid-filled loops called the semicircular canals. These loops act as an internal gyroscope. Whenever you tilt your head, the liquid trapped inside these specific canals sloshes around, reacting to gravity and the angle of your movement. That fluid movement constantly feeds real-time telemetry back to your brain, reporting your exact posture and your body's specific position in 3-dimensional space. Without this silent, uninterrupted stream of spatial data, humanity would lack basic equilibrium. We would be completely incapable of running, dancing, or even standing upright on 2 feet. The precision of this dual sensor system comes with a major biological trade-off. The microscopic engineering that makes the ear so advanced also makes it highly vulnerable to physical stress. Today, we routinely subject this delicate machinery to heavy strain. Extended daily use of earphones, whether studying for hours or commuting in noisy environments, pumps continuous pressure directly into the ear canal. This sustained stress exhausts those microscopic hair cells in the cochlea. Over time, that exhaustion leads to tinnitus, a permanent, unyielding ringing sensation, or even irreversible hearing loss. To prevent that damage, audiologists recommend a specific safety protocol, shown here, the 60-60 rule. This requires capping your device's volume at a maximum of 60% and enforcing a strict rest period for your ears every 60 minutes. Beyond volume, there are physical hazards to avoid. Inserting objects like cotton swabs deep into the ear canal puts you at direct risk of puncturing the highly sensitive tympanic membrane, instantly destroying the start of the amplification chain. When we treat the ear as an irreplaceable, highly sensitive radar system, we can properly protect it. Doing so guarantees a lifetime of acoustic connection and physical stability.